Okay, so I'm going to get started. I hope you guys all had a good break. I know it's rough being here at 9 a.m. the Monday right after break, but let's get back into chemistry. Okay, so exam regrades, I did those over break. You should have seen your grade change if you got points back. Those are being distributed back to the TA, so you should be able to pick it up in recitation this week. Quiz number 3 is also in recitation this week, so everything up through the Friday before break is covered. So all of chapter 20 could be on there. The first little bit of chapter 21 might be on there, so we got like halfway through page 2 in the notes. Or anything before that might also show up there if, you know, there are some spots that I wanted to emphasize from previous material. Okay. And then Sapling chapter 20 is due this week. I think I updated the due date to 9 a.m. Friday, and now I'm not sure if I hit save now that I think about it. So it will be updated to 9 a.m. Friday if it isn't already. But yeah, we finished chapter 20 Friday last week, the week before break. Okay, questions about that? Okay, cool. All right, so where we are at is looking at carboxylic acid derivatives. So sort of a quick refresher that's not in the notes, but just to get everyone back up to speed. I guess it's earlier in the notes. Okay, so we're looking at a whole bunch of carboxylic acid derivative reactions in this chapter, and pretty much all of them follow the same 2 basic steps. Which is you start with a carbonyl with some kind of heteroatom type group on there. You bring in some nucleophile. You break up the carbonyl temporarily. And for a little while, you're taking the central carbon from sp2 to sp3 hybridization. So this is the tetrahedral intermediate. And then O- or possibly neutral OH, depending on the exact conditions, can kick back down and boot out the Y group, or X group. Jeez. All right, so we're swapping out X for Y, whatever those 2 groups are. All right, so this is like the core of all of the mechanisms, or most of the mechanisms that we're going to see in this chapter. But there may be a bunch of additional proton transfer steps. So this is kind of context dependent, and this is where all the mechanisms vary. Like if we're in acid, we're probably going to protonate the carbonyl first, and there might be difference in charges, like instead of attacking with a Y with a minus charge, we might attack with like a neutral Y that has an H on it, and then that would need to get deprotonated at some point, and also like this would now be an OH if we protonated it first. And we might need to also protonate the X group before we kick it off. So a lot of that kind of depends on exactly what the details of the groups are and what conditions you're in. But as long as you think of it in terms of like pKa's, like is this something that's likely to protonate in acid, or is this something that needs to get deprotonated to become, a stable neutral group that just added on, or is this something that needs to get protonated to become a good leaving group, then you should be able to pretty much figure out all of the mechanisms for the main part of this chapter on your own without even like memorizing everything. Just start with this, and then if you want, like, you can even just draw out this core part of the mechanism and flesh in some details depending on exactly what's going on. So we went through one example for acid catalyzed ester hydrolysis. So let me go through that as like a direct comparison with this core mechanism. So you know what, I don't remember if I did in this lecture acid catalyzed amide hydrolysis before I ran out of time. Do you guys have that in your notes? Yeah. Okay. Okay, maybe I guess like the base catalyzed version is pretty much identical step for step with all of these, just because, well, there is actually one extra proton transfer step. So I think I did not get to base catalyzed amide hydrolysis in this section. I think, yeah, that's right. Okay, so let's do that as an example. Okay, so base catalyzed amide hydrolysis. Okay, so we're starting with an amide. And we're in base, so there's no extra protons around. Okay, so I guess one other thing that might be helpful to remember is hydrolysis also just means reaction with water. So basically H2O is going to be one of the reagents, and then in base there's also going to be OH minus. If we're using acid, we would also have H plus. And we could write that combined with water as H3O plus if you want, or you can leave them separate, doesn't matter. Okay, so reacting with water in base. So these are the reagents that we have for base catalyzed amide hydrolysis. We don't have any spare protons around, we're in base, so we're not going to protonate the carbonyl or anything to get things started. But we do have a good nucleophile, so this can just go straight in for the attack. So this is actually pretty similar with aldehydes and ketones, where we could do base or acid catalyzed, say, hemiacetal formation as one example, where we don't have a great electrophile. We're not protonating this thing, but we do have a pretty good nucleophile. Okay. So here's the first of the two sort of key steps of the mechanism, where we make the tetrahedral intermediate. Okay, so we get to here, and then even if we don't have any idea like exactly what the steps are going to be, we can still figure out, okay, we do not need to deprotonate this, it's already neutral. We don't really have any surplus protons around to protonate this thing, so we're just going to go straight in for the step where we kick it out. The downside to doing this is that we're kicking out an NR2 with a minus charge. Does anyone have sort of a ballpark feel for about where the pKa of this guy is? Yeah, it's pretty high. It's like mid-30s-ish. The exact number depends on what the R groups are, but yeah, we're kicking out like a reasonably strong base. So this part is actually going to slow the reaction down quite a lot. Depending on what source you're looking at, some books will actually show, to avoid making a nitrogen with a negative charge, they'll actually show the nitrogen getting protonated first. It's kind of a toss-up between two not great options. One is we kick out a really strong base. The other is we magically pick up a proton from somewhere in an environment where there really aren't any available. Either way that you show it, I'm going to stick with this way because I think this is how Loudon does it. But either way, we have sort of a difficult step to do here, which is why, if you remember, amides are less reactive and more stable than a lot of the other carboxylic acid derivatives. And this is a big part of why that leaving group doesn't really want to get off of there. So they're more resistant to hydrolysis. Like, you can still make it go, but it's going to take higher temperature and longer reaction times. Okay, so I guess it's sort of a comparison. What really matters is we made a base with pKa 36-ish, and we're using up a base pKa about 16. So that's kind of a big jump in how basic the thing is. But the trade-off is that this thing doesn't have to sit around for very long, because we also made a carboxylic acid here. So even though it's going over like this huge high peak in the energy diagram where it's making this base that it's very unhappy about creating, it doesn't have to stick there for very long. It can just rip a proton off of the carboxylic acid that it just made. So everything works out okay in the end. You end up with this nice stable amine, and you end up with this thing, pKa probably somewhere around 5-ish. Okay, yep.
So can you only form a carboxylate in these base catalyzed?
Yeah, so pretty much every time you're in base conditions, the last proton transfer step is probably going to be ripping a proton off of the carboxylic acid that you just made, which sort of makes sense. Like, even if you weren't doing a reaction, if you just chucked in some carboxylic acid into basic conditions, it would get deprotonated anyway. So, yeah, good question. So if we did want to get the acid back in its neutral form, then we could do, so like water might not be enough to convert it fully, but if we did H3O plus as the final step, then we would get the neutral acid back. Yeah, so sapling is actually, I think they have one or two questions for this chapter that are actually like a little bit nitpicky about when you show the final products. If it's in base and they don't include an acid workup, then you have to show the final product as the actual negative charge form. Uh-huh.
Will we have to worry about the carbon getting reprotonated when we have the H3O plus?
Yes, but not like permanently. So the equilibrium still favors this thing not having a proton on there. It's just like as the first step of a mechanism, some of the time it's going to get protonated, and then if you have other things that can happen, then that sort of starts it going. So, yep. Mm-hmm.
Second step, isn't there a risk of that oxygen going and protonating ammonia?
Yes, but so I guess like what you're asking is, why wouldn't this just like go pick up an H and then you have this carbon with 3 different kind of groups on it? That can happen some of the time. I think the reason why it never stays at the tetrahedral intermediate for very long is, I think, ultimately just down to the carbon-oxygen double bond energy. Like, it just turns out to be more stable to have the carbonyl in the long run, especially when you've got 2 leaving groups here. I guess what's a lot more likely than kicking out the nitrogen is this OH adds, and then it just gets immediately booted back out again. So instead of kicking out the nitrogen, you just kick out the OH minus, and then you're back where you started. And based on the pKa values, that probably happens like thousands of times more frequently than the nitrogen getting kicked out. It's just we can't tell because nothing changes in that case. So, okay. So questions about that? Not just like the specific mechanism, but like how I'm sort of basing it off of this and then just adding proton transfer steps as needed as I go along, kind of. Because knowing how to do that will save you so much work in this chapter. Yeah. Uh-huh.
Like, when do you know when it's proton transfer?
So a lot of it comes down to, if you're an acid, probably stick a proton on there first. and then so like protonate the carbonyl to get things started, and then the rest of it comes down to you know, if you attacked with something negative, then it's neutral afterwards and you don't have to do anything to it. But if I had attacked with something neutral here, like if I used water, then I would have to deprotonate it afterwards to get it to neutral. So it's sort of a question of juggling, like, you know, I want things to be neutral afterwards, but if I want them to leave, then I may have to protonate them first if I can. So, I guess it's not really. So water like is the solvent, but really OH minus is kind of doing the actual attack. So yeah. Okay. Yeah, I guess you could sort of view water as like a proton transfer like mediator. So like maybe if this nitrogen got kicked out, it would go protonate itself off of water first, and then water could sort of get a proton off of the acid later. I guess proton transfer is kind of a poorly defined step, so as long as you end up at things that make sense based on pKa, then it's not too picky. Yeah. And there are actually like kind of like other sources show this happening with a slightly different ordering of steps. Like if you show it this way on the test, that's cool. If you show it like protonate the nitrogen first from water, which some textbooks do, that would also be acceptable. So there is like some leeway as long as you're doing things that are not completely unreasonable, basically. Yeah. Okay. So other questions about this? Okay, cool. So one more mechanism that I'm going to look at for hydrolysis is the most stable of the carboxylic acid derivatives, which is nitriles, because there we have a little bit of extra work to do. Okay, so let's do this in acid first. Okay, so it helps to think of this as like sort of a really unreactive version of a carbonyl. Like instead of a CO double bond, it's a CN triple bond, but it still does some carbonyl-y kind of things. It's just a very small delta positive on this carbon, so it's not as electrophilic as it would be if it were a carbonyl. So in acid, we have, as a reminder, H2O and H plus for acid catalyzed hydrolysis conditions. So we're going to get this started by protonating the nitrogen, just like we would protonate a carbonyl if we were in acid. And then, just like if we're doing an acid catalyzed, say, ester hydrolysis, we would go attack the base of the carbonyl with water. I'm going to sort of bend this up out of the way a bit. Okay. So at this point, I guess in the notes I kind of show it as two separate proton transfer steps. As a reminder, anytime you need to lose a proton from somewhere and gain a proton somewhere else, you can show that as one step or two. I don't really care. I'm going to show it as two steps just to be consistent with how I have it in the notes, because this intermediate, if you show it like pausing here in the neutral form, actually has a name for that functional group, and that is an imidic acid. It's sort of like a carboxylic acid, only it's made of an imide instead of a carbonyl. So that's where that name comes from. Okay, so we took off a proton, and now let's pick up a proton. And, okay, so right now we have a double bond to a nitrogen, we have a single bond to an oxygen. It helps to keep track of where we're headed. Ultimately what we want is a double bond to an oxygen. So if you sort of keep that, I guess, landmark in mind through the mechanism and use that to figure out where we're heading, that might make it easier. So it turns out once we protonate the nitrogen, we can have the oxygen sort of do what's basically a resonance form, actually. I think I show it as two separate steps in the mechanism, but really if you look at it, we're actually just doing resonance to get here. And oh, look at that. We have something that's basically like a rotated picture of an amide. It's a carbonyl with an NH2 on it, only we just have a proton on the carbonyl that we need to get rid of. So this is where something could come in, take the H. I guess in the notes I show water doing it, but you don't have to be that specific. Okay, so this is an amide. And then from here, it's just amide hydrolysis. And so ultimately, you're going to get to the straight carboxylic acid. Okay. And then, I guess as a byproduct, you also get NH3 getting kicked out, which, given that we're an acid, is immediately going to pick up another proton and become NH4 plus. Okay, so kind of a similar mechanism with the added twist of you can do resonance and sort of switch which atom has single and which has the double bond partway through, and then that gets you to a mechanism that we've already looked at. So it's kind of a longer one if you show it all in one place, but the second half of it is something we've already done. Questions about that one? Mm-hmm. Good question. So given what we know of how reactive nitriles are compared to amides, like which one, I guess, is going to be slower to do the hydrolysis to start things out, do you think? The nitrile, right? Yeah, so like this step, all of these steps are slower, and then once you get to the amide, it's more reactive, and it'll go faster. I guess if you're super careful and like monitor the reaction on like TLC or something, you might be able to like stop some of the molecules at the amide, but I don't know how tricky or finicky that would be. Probably pretty difficult to like stop it partway, I would guess, yeah. Good question though, like, but yeah, sometimes it's just too fast once it gets to the halfway mark, I guess. So, okay. So other questions about the acid version of this? Okay. Okay, so then as one more one for this section, let's look at the base catalyzed version of nitrile hydrolysis. Okay, so again, hydrolysis, we're going to use H2O, and now we have OH minus in there. Okay, so we've got the nitrile. Just like the other base catalyzed mechanisms we looked at, we don't really have any protons around to protonate this to get it started, but we do have OH minus, which is a decent nucleophile. So this can actually just go straight in for the attack. And we're actually running into the same kind of issue that we saw in base catalyzed amide hydrolysis, where if we do that, we're getting a negative charge on nitrogen. So this step is very pKa disfavored. I'm not 100% sure, but I think some sources might also show the nitrogen here getting protonated first, just from water. But I think our textbook shows it picking up a proton from water after that happens. But if you show it in either order on the exam, we'll accept it. Okay. So here we are at the amidic acid again. So we're still hitting the same intermediate. We just took a sort of different route to get there. We had minus charges popping up instead of positive charges. Okay. Now we're here, and we can't protonate anything like we did when we were in the amidic acid and acidic conditions, but we can deprotonate. So let's do that. Okay, so again, you could show two resonance forms of this. One with double bond O, one with double bond N, kind of like over there. The difference is here, one of them has a very clear reason for being disfavored, like negative charge on N is a lot bigger deal compared to negative charge on O. Versus over here, both of these are at least like closer to each other in energy. The positive charge is not as unstable on one versus the other as the negative charge is here. So probably showing it in this form is probably the more realistic option, which is why that's the only one I show in the notes. Okay, so to redraw that down here. So instead of showing this thing going and picking up a proton, I'm just going to go straight into it from this resonance form. Okay, so this is this thing just redrawn. Okay, and that again gets us to to the amide, which from there we can just do base catalyzed amide hydrolysis. Okay, and so in the long run we're going to get briefly the carbonyl, the carboxylic acid, but we're in base, so you know a proton transfer step is going to happen right away. And then we're also going to get NH3 kicked out as well. Okay. So any questions about this one? Okay, yeah.
So when you're in the resonance step here,
Mm-hmm.
is it difficult to move to the protonation or the protonation step if you have like spectator ion? Like, is that resonance the one on the left favorable enough that you have to like add heat or something to move on in the reaction?
Not really. I guess so I guess really what we're looking at is the difference in pKa's between like this O- form and the one that I didn't show that we're forming is sort of a byproduct of this step here is we made a molecule of OH- by doing this. And those are pretty comparable in pKa's. So like this one might be several units lower just because it's got resonance available to it, but the resonance is kind of minor. So I'd say like it should be kind of a wash. Like this step I don't imagine being like too terribly difficult, but it's not super favored either. So yeah. Okay, good question. Okay, any other questions? Okay, cool. So let's see. So I guess the last two hydrolysis things, I'm not actually going to show the mechanism for. This might be sort of a good opportunity to practice. I might give you like a step or two to get you started, but okay, so and that is the two reactive ones, acid chlorides and anhydrides. So these are more reactive, and they don't actually require acid or base. They just need water. Which makes sense when you look at it, right? Because if you, so you're doing this reaction. So normally for like esters or amides or what have you, you would have to like protonate this first to make it attackable enough that a neutral nucleophile could come in and do the job, or you would have to use a strong nucleophile to come in and attack. But one way or the other, for esters and amides, you have to sort of make the reaction look more enticing by catalyzing it with acid or base. Here, we know this has got a huge delta positive on it. It's already attackable enough as is, so you don't really need to add anything to get things going here. So I don't need to protonate it with H+, or use a good nucleophile like OH-. Water is totally adequate for the job as is. So you can just straight up go right in there with water. I guess this one's short. I guess I don't have it in the notes, but I'll do it anyway. Okay. So this step might look a little bit unlikely to you because we are making something with a negative and a positive on the same molecule. But this step was so favorable, we're attacking something with a pretty huge delta positive charge, and so this actually ends up working out okay the way it is here. And then I guess we've got a couple options on the exact ordering here. At some point we're going to have to deprotonate this water molecule that attacked, and at some point we're going to have to kick this down and boot out the chlorine. You could show those in either order and it would still make sense. Let's do the proton transfer step first. And note that you could also show an intramolecular proton transfer. And then deprotonate at the end. I'm actually not sure which of those is most likely. Let's stick with doing it this way. Okay, so I guess sort of as a bigger picture, sort of addendum to that, like sometimes you know a proton transfer step has to happen at some point to get something to be neutral, but you're not exactly sure what order things are going to happen in. In that case, a lot of the time, multiple different orderings might be okay, as long as you get the step happening in there sometime. It makes sense overall, as long as you're not creating anything extremely unreasonable in the meantime. Okay. So then kick down, reform the carbonyl, and get to this thing. Notice also that on the way there we lost a proton to a molecule of water. So we're actually creating what's basically HCl reacted with water as a byproduct. I guess that doesn't matter for this reaction, but it will actually matter for a reaction that we'll look at later today, where we need some way of absorbing HCl. But for this particular one, it's not like that's going to mess up your products in any way. So at this point, we're done with the reaction. Yeah?
You need a lot of water added to drive this forward because it's the second step and it seems like that just revert back to the first easily.
Yep, so it turns out the delta positive on that thing is so big that even like traces of water from like atmospheric moisture will unfortunately do this. which is why you usually want to keep acid chlorides capped as much as you possibly can. So yeah, like it does seem unlikely what you're doing in the first step here, but it turns out the delta positive, getting rid of that is a bigger driver. So, okay, other questions about this? Okay, I guess one other thing that's worth pointing out is you are making a carboxylic acid by doing this, so you could sort of consider this reaction to be in like acidic conditions for every molecule after the first one does this in like a given bottle, but so I guess you could start this off with like the carbonyl getting protonated, and then you would avoid this sort of Zwitterion, I guess, yeah, this is a Zwitterion, kind of intermediate. So that might be another way to show it, as long as you're sort of doing all the things that need to be done, like you're protonating at some point and deprotonating at some other point in the right places. Okay, other questions about this? Okay, cool. And then, okay, so that's acid chlorides. Anhydrides are pretty much the same thing, only instead of kicking out a chlorine. So here's your leaving group for this reaction. The chlorine gets booted out with a minus charge. And then here's your leaving group for this reaction. The entire other half of the molecule gets booted out with a minus charge. So I guess if you wanted to show the byproducts, it's Cl minus versus this carboxylate as a leaving group. Okay. So that's pretty much it for hydrolysis. The mechanisms, all pretty much the same deal, and there's a lot of flexibility in what you show happening when, as long as you're not doing anything unreasonable. So focus more on like knowing what needs to happen than on just memorizing like this goes to here and then that goes to there kind of. Look for trends, I guess, rather than memorizing individual sequences. Okay, any questions about this section as a whole? Okay, cool. So the next section we're going to get into, so I guess hydrolysis is kind of sort of useful. It's a way to get everything converted back to its parent carboxylic acid, and then we can access all of the chemistry out of chapter 20 because we know some things to do about carboxylic acids. The rest of this chapter is going to be about not going back to the acid, but it's going to be about converting between two different carboxylic acid derivatives. So maybe instead of going from like acid chloride back to the acid, we might go like acid chloride to amide or acid chloride to ester, for example. Okay, so reactions with acid chlorides. It's worth pointing out, so acid chlorides are the most reactive out of all the derivatives. And so it's actually pretty easy to access like any other acid derivative if you start at the acid chloride. So a lot of the time, a question? Mm-hmm.
Sorry, I was just looking at the last mechanism.
Mm-hmm.
If Cl minus and H3O plus put together, could you form H3O plus in water, or is that not going to happen?
Oh, sorry. Could you form HCl, you mean? Or yeah. You can, but I guess then if you look at the pKa's, like it's way more in favor of like, so I guess what you're asking, let me do a little box down here, is like H3O plus and Cl minus. And then this is like a pKa problem, kind of a setup where you've got like HCl and H2O. And it turns out, based on pKa's, the equilibrium just kind of strongly favors the Cl having the minus charge. Okay. Yeah, good question though. I guess like, I forget what the pKa of HCl is. I think it's like -4-ish or thereabouts. So it's not like that huge a difference in pKa units, but it is still favoring this side. So, okay. Good question. Yeah. So I guess like for a lot of the reactions in this section, it may help to have the pKa table pulled out and just sort of check that what you're doing is reasonable. Okay, so acid chlorides, since they're the most reactive acid derivative, a lot of the other derivatives are the easiest to get to if you start at the acid chloride. So in a synthesis, a lot of the time your best option is not to react straight from the acids, so not to do some of the reactions we saw in chapter 20. A lot of the times your best option is to go from the acid to the acid chloride. And from there you can sort of drop down in energy to any one of the derivatives that you want to access. So like esters or amides or nitriles. I guess you can do anhydrides too. I don't remember. Oh yeah, I do that one. Okay. So synthesis-wise and in the lab, a lot of the time, you don't really want to start with the acid. You just want to convert the acid to the acid chloride first, and that gives you the flexibility to go wherever you want. As a reminder, SOCl2 is what we're going to use for that. Okay, so a lot of this section is going to be like, once you've converted the acid to the acid chloride, what all can we do with that and how do we make it happen? And the answer is, this is reactive enough that pretty much we just need to expose it to whatever the other half of the group is, and maybe do a little extra work in the case of nitriles. So for example, if we want to make an ester out of this, we just have to bring in like an HOR or ROH molecule. And then that'll turn it into the ester pretty easily. The one downside is we're making one equivalent of HCl by doing this. It might not exist as actual HCl, but it's still, you know, an acid and a chlorine. So a lot of the time, we're going to need something to soak up the HCl. We've actually seen a little bit of this in the past when we used, back in OCHEM 1, when we used SOCl2 to convert alcohols to chlorines. That was when we used pyridine. Which, as a reminder, is basically benzene, only one of the carbons replaced by nitrogen. Okay. Some other options that you might see, so triethylamine might show up here. Nitrogen with 3 ethyl groups on it. ET3N might also be how you might see it. And the reason that these are used is because they're good at reacting with excess acid, or HCl specifically in this case, but they're sterically hindered enough or non-nucleophilic enough that they're not actually going to try going in and reacting with the acid chloride themselves. So they're just mostly there as a spectator, except when there's some acid that needs being absorbed to pull it out of the reaction. Okay, so let's look at some examples of how this might work. And the control panel just totally locked up. Cool. All right, well, let's see if I can move the camera over later. Sorry to whoever's watching this recording later. All right, so we have an acid chloride. If we want to make an amide, we're just going to combine it with the other half of the amide that we want to make. So nitrogen with the two R groups on it, and then for it to be neutral, we have to have a proton on there. Okay, so if you want, you can figure out the mechanism for this. It looks a fair bit like the hydrolysis mechanism, only instead of water, we're using amine. But we are making one equivalent of HCl by doing this. And the problem with that is that we still have a bunch of amine around, which is going to get protonated. That may or may not be a problem. I guess it's definitely a problem if you're using only one equivalent of amine. So basically, for each equivalent of amine that you do this reaction with to make the amide, you're also burning through another equivalent that gets reacted with the HCl. And so half is going to make the amide. And half just gets wasted on soaking up HCl. So the workarounds for this are either use two equivalents, or add one equivalent of amine that you want to add and one equivalent of one of these sacrificial bases, pyridine or triethylamine. Okay, so you might see this reaction written as two of those goes to make the amine. Or you might see it written as HNR2 and, for example, pyridine. And that would get you the product too. And which of these options you use really kind of depends on how expensive the amine was to begin with and what the R groups on it are. Like if this is some small cheap amine that you just bought in a bottle, then you can probably just waste half of it and no one cares. If it's some big complicated thing with a bunch of R groups that you spend a bunch of time and effort on, you probably don't want to just throw away half of it to soak up some HCl. So that's when you would use a sacrificial base. Okay. Questions about that one? Okay, let me see if the camera is working. Okay, no. Okay, so that's how it works making an amide from the acid chloride. Any questions about that kind of set of options? Okay, so esters are pretty similar. but normally you're just going to use pyridine. So you might see this reaction written as this ROH and pyridine gets you right to the ester. Okay, so the reason why we can't do the two equivalence trick here is that alcohol is not as great a base as amine was, and so it's not going to be as good at soaking up HCl. So if we really want to make sure the HCl is not hanging around and causing problems, we'd better use a sacrificial base instead. Okay, and then one more for this section. How much time I got left? Okay, I'll do one more real quick that's pretty much along the same lines, and that is anhydrides. Again, we just want to bring in the other half of the molecule. In this case, we're actually going to bring in something that's a little bit more nucleophilic than the other two. So we're actually bringing in the negative charged version of the molecule. And that's because carboxylic acids are really crappy nucleophiles, and so we want to sort of give this thing a little bit of a boost for it to go in a reasonable amount of time. But then just like before, this thing comes in, attacks, kicks out the chlorine. If you want, you can sort of work out the mechanism for that as practice. And we end up making this. So I forget who asked it before break of can we make anhydrides where the two sides are not symmetrical with each other. Turns out yes we can, but we can't go at it direct from the acid. We got to come at it from the acid chloride and the carboxylate. Okay, so I'm going to pick up from there next time.